So I want to abuse the notation just a little bit. And I'm going to say, well, I can also write this as saying that the radiance, in this particular case, same as before, but now I'm using, I guess, what I'm calling a vector delta function, right? So what we said before is that I only see a reflection if the viewing angle is exactly the mirror angle, right? So essentially, these two things would have to be the same so that I'm lined up in exactly the right spot. Another way of writing that is that the half angle is the same as the normal, right? So another way of saying that is if the vector that's exactly halfway between the sensor and the light is the same as the normal, then you get a mirror reflection. And that would be for sort of a single perfect point. So that's the mirror BRDF. Most things that are shiny are not perfect mirrors, but we can think of them as being glossy, okay? And what the glossy means is, if we have our illuminant here and we're coming out some angle, it means I don't have light just at the mirror point, but it's spread out a little bit, okay? And that's what this lobe here is meant to show, okay? And the more gloss, as opposed to being specular, right, blurrier, I make that lobe a little bit fatter. Okay? And that's written as this equation, which says that basically, now instead of doing that delta function, I just take the cosine of the angle between them, all right, m dot v, raised to some exponent, okay? Because that's the angle between them, and I raise some exponent. Now, if the angle between them is 0, that means it's the perfect mirror angle, right? Then that dot product is 1, raised to a k, it stays 1, and I get a perfect reflection. But as the angle falls off a little bit, cosine becomes a little bit less than 1, and when I raise a number less than 1 to the k, well, as k gets bigger, that falls off faster, okay? And in fact, you can see that illustrated here. These are some artificially generated images. So here it's just, moving the light source to different directions, okay, not so exciting. Here, you can see that the specular component is getting tighter and tighter and tighter. All right, and so it's getting more like a mirror, and that's the raising of that K, okay? And so that's the specular component. And in computer graphics and in computer vision, what we often do is we combine that diffuse and the specular, and it's referred to as the Phong model, because Phong was one of the first people to do it. Then there's the Blin-Phong model, and there's lots of models that have increased beyond that. But the idea basically is you say that you can model the BRDF of lots of surfaces as a combination of a Lambertian plus a specular. So we have the Lambertian, which is everything looks equally bright from all directions. That's what these equal-sized arrows are meant to show you. Remember, the light doesn't go out equally, it just looks equally bright. Plus the specular model, whose sort of blur amount is defined by that fall-off. And when you combine those, you can get sort of the matte plus the specular. And here's an example of some recovered imaging where here you have a original image, and here you've sort of broken it down into the matte components and the specular components. Likewise here, you have this object that has the matte surface, that's the paint itself, plus the glossiness of the varnish, or whatever it is. What is it you put on top of ceramics to make it glossy? Gloss. Gloss. Thank you very much. Okay, and the idea is that this is the matte component, and again, this is the specular component. And the ability to pull those out is a computer vision problem. That's all the physics we're going to do. We've talked about how we model the light, and we talked about surface properties, so the albedo of the matte reflectance and sort of the specular component. And we've talked about how the shape, the surface normals, interacts with that. So in computer vision, there are these fundamental questions of, well, when I look at a scene, can I figure out, say, the shape or the albedo or both just from an image that I'm looking at? And so fundamentally, this is an ill-posed problem, right? Because it's an interaction between both the shape and the whatever's painted or the texture on the surface. And yet our brain does it all the time, which means that we as computer vision scientists, we'd like to try to do it too. So over the next couple of lessons, we'll be talking sort of the computer vision approach to recovering those elements. All right, welcome back to computer vision. Last time, or whenever it is you chose to watch it, the last thing I talked to you guys about was how surface appearance involved the interaction between the lighting and the surface itself and the shape. So that's what it says here, that the image intensity that we'll see will be a function of the lighting or the illumination, the surface reflectance, and then when we say the shape, what we actually mean is sort of the surface normals. That is how the shape is, how the surface bends depending upon its direction with respect to the illumination. And so one of the challenges that this poses is, if you wanted to recover, say, one of these, like you wanted to recover the shape, or you wanted to recover the reflectance of what's there, you know, the texture or how bright it is, in some sense you can't do one without knowing the other. And this is a classic example of what's referred to as an ill-posed problem in computer vision, that in some sense you can't do it without making some sort of assumption. And a simple example can be seen here. All right, so what do you see here? What you see is an image stolen from the web. But probably what you're seeing is you see some sort of matte or light textured sphere with a light shining probably from, say, this direction here. You might even see that there's this little ridge in it there, and then the light falls off, and then there's this shadow cast here. Is that what you see?
Yes.
But actually what's really there, of course, is this very flat monitor with different pixels that are sort of violating the whole illumination thing, because they actually emit light themselves, which violates the entire principle of what we were saying before. And in fact, your stereo, right, my two eyes are looking at this thing and saying this thing is totally flat. And yet my brain says, okay, yeah, there's this nice rounded thing there. In general, what your brain has to do is to make a whole variety of assumptions in order to disambiguate between different possible solutions, that is, different possible interpretations, in order to come up with one that it really likes. And in fact, your brain does this so well, you don't even notice that it's doing it. A colleague of mine, Ted Adelson, is sort of a master at exploring these kinds of things, and he's put together some really compelling demonstrations of your brain making assumptions in order to determine lightness. So one of them is here, right? So this is a relatively simple scene, and you see the two squares marked A and B. And if you look at it real carefully, you'll say, oh yeah, A is a dark square and B is a light square, right? And this is so mind-blowing, because even though I look at this all the time, I can't believe it, all right? You ready? So here's this gray bar, nothing up my sleeve, okay? And you'll notice that gray bar is a constant intensity all the way along, right? It's the same intensity. It's not like it's lighter and darker. And now we're going to move that gray bar, and it's lined up with square A and B, and yet there's no edge here, and there's no edge there. See, I'll remove those lines. So A and B are actually the same intensity, okay? And when you look at it, you swear they're different intensities. In fact, here I put two gray bars there, right? And now, depending upon how far away if I kind of squint and I ignore all the rest of it, I can see that all of these squares are the same intensity. But it's just, incredibly hard to see that. So what's going on there? Well, clearly what's going on, a couple things. One is my brain is compensating for this shadow, right? So it's seeing this shadow cast by the cylinder. So it says, okay, wait a minute. If there's more light here than there is there, then this thing, if it's the same intensity coming off the image, it must be a lighter square. The other thing is that the idea of this being a lighter square is consistent with this interpretation that this is our checkerboard and these are nice light squares and the repeated pattern. And generally, the way I like to think of it is your brain likes consistent interpretations. So this is sort of compensating for the shadow. Your brain saying, okay, I see that shadow, I understand that shadow, so the thing underneath it must actually be lighter, even though the image intensity coming up at you is the same between A and B. So here's another example, also from Ted, that your lightness perception can be influenced by three-dimensional cues. That is your belief about the underlying shape. All right, so here we have two squares there, and those probably look like they're the same intensity to you, and in fact they are, as the gray bar there shows you. But now we get to blow your mind again. You ready? Here we are. Okay, those two squares, and now you're saying, no, not possible. It cannot be that those two squares are the same intensity. Well, here comes my bar. And there it goes. I love this. And son of a gun, it's the same intensity, right? In fact, let me back that up, right? So this square and this square are the same brightness. And when you look at it just like that, You just don't really want to believe it. And then when you put it next to the gray bar, you realize that it's true. So that's your brain, again, interpreting that, okay, this area is in a more shaded area than that area. So this square, even though it has the same intensity as that, because it has less lighting falling on it, it must be brighter. Okay, so again, it's your brain making these kind of assumptions. And there's a very simple demonstration of this called simultaneous contrast. And so if you're looking at this, and it may depend a little on the setting of your monitor, you probably see this square as darker than this square, even though, of course, they're the same intensity. And the idea is that your brain sort of focuses on these contrasts. So your brain is doing all these kinds of things in order to try to figure out what lightness is.
So we see that the lightness that we perceive at a location xy is a product of R and E, where R is the surface reflectance affected by the color, texture of the object, and E is the incoming light energy or irradiance affected by the brightness of the light source and the angle between the incident ray and the normal of the surface. Okay, now out of these two, which one do you think varies faster or more frequently with changes in location, and which one varies slower or less frequently? Type in your answers in the boxes. You should say more in one and less in the other. Okay, take a look at this image as an example. See how the appearance of this wall, which we can assume to have constant color, varies gradually due to lighting. But look at the features in this image. These are created due to reflectance or color variations. So we can expect reflectance to change more frequently with respect to the location compared with irradiant light. There are, of course, other elements to consider. For instance, object boundaries and shadows. Sharp edges can also affect observed lightness. These factors definitely complicate things, but realizing that they change more or less frequently or in different ways forms the basis of identifying and ultimately separating these factors while observing an image.
In some sense, you might think that the visual system is making a mistake, right? I mean, after all, these two squares have the same amount of photons hitting your eye, and yet your brain says, no, that one is made out of darker stuff than this one. But of course, what's actually happening is your brain is sort of decomposing this problem into the amount of illumination and the underlying reflectance. Let's use this example to frame the problem a bit. First of all, we're going to assume that we have a Lambertian surface. And what we mean by a Lambertian surface, remember, is just the lightness that will come back to the camera. And I'm just going to use the term lightness. I'm not going to use radiance or irradiance, etc., because I don't want to worry too much about that particular physics. Basically, I just want to talk about the lightness that the camera sees as is being a function of just three things. The I is just the power of the illuminant, the strength of the light. Rho is the albedo. And then there's this theta angle, and the cosine of the theta determines the brightness of it, and it's just the angle between the illuminant and the normal, sometimes called the incident angle, because it's the incident angle. The problem is we have this ambiguity, all right? Let's combine both the angle and the strength of the illuminant into a single term, E. Just think of that as energy or something like that, right? It's the amount of energy incident on this. We've already taken into account the cosine angle. And then we also have some reflectance function. Maybe it's just the albedo, R. So the brightness at any point of time is equal to this product of the reflectance times the energy, R times E. So L is equal to R times E. So we can think of it this way, right? E is the amount, is the sort of the appearance of a white piece of paper with the given illuminant, right? So if you were reflecting everything everywhere, E would just be what it would look like if I had a white piece of paper. Likewise, R, the reflectance, if I just had a constant white light, all right, we're not worrying about color, but it's constant light, it's sort of the planar patch. That's what the reflectance is. And L is what we see, all right? And the problem is, if we measure L and we want to recover R, the question is, how is this possible? Because we might not know E, right? So E can vary, right? It can fall off, you know, because of the shadow, etc. So the question is, how can we do this? And the answer to do this is we have to make some additional assumptions. So some assumptions I'm going to tell you now are the ones that we're going to use to drive a particular computational theory. It's not clear exactly what assumptions